Jai Hind all. This is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College, EC Department. This is a lecture series on VLSI technology, course code KEC053. We are discussing the complex topics which are required for completion of the general topics, the topics of the syllabus, but are not available directly in the syllabus. So, the today's topic is the damages during the deposition. In the second unit, we have created epitaxy layer, and in the third unit, we have discussed diffusion and the ion implantation and the deposition processes. So, this topic is related to those all topics where we have deposited a layer. So, we will discuss the layers, the damages that occur during the this deposition. So, in the epitaxial, in the previous lecture, in the main lectures, we have seen that we have ingot formation that we have done in the first unit, in the first first 4 units, 4 lectures. We have discussed wafer preparation through ingot. Then this wafer is again grown by some another layer, which is known as the epitaxial layer. So, epitaxy involves the extension of the substrate that are grown by the wafer, so substrate lattice, by overgrowth of a layer of the identical or the different material. We have also seen that if the material is the identical, it is known as the homoepitaxy, or if the material is different, then it is the heteroepitaxy. So, for the fabrication of the different applications, for example, for the fabrication of BJT, the only crystal form is a crystal form that is done through the wafer is not appropriate. We have to do uh, other layers like epitaxial layer for the well shaped structure. Uh, So, we have to take the epitaxial layer for to grow the layer that is used to create a well shape. Epitaxial is generally we can say that it is acted upon a layer, or we can say it is a arranged layer over the bulk layer. So, we grow epitaxial layer over the bulk crystal. The main difference between the two layers, the epitaxial layer and the bulk layer, is that the bulk layer's thickness is very high. It is approximately 500 microns as given here, whereas uh, it is 100 the epitaxial layer is 100 times thinner than the wafers. So, it is approximately 1 microns or 0.5 micron or even lesser. So, thin crystalline layer that is grown over, arranged upon the bulk crystal, is called the epitaxy, in which we deposit another substance over the wafer. According to the deposition, we can say that it is hemiepitaxy or the heteroepitaxy. The first thing that comes with this epitaxy is the junction shift. Junction shift is there when we say that there is a particular junction, but that we draw actually a metallurgical junction, but electrical junction is different. So, if we have a device, let's suppose a PN junction, we draw it like this one, P and N. Here it is a junction, but if we see actually this junction is shifted from the actual position. So, the metallurgical junction that we drawn over here and the electrical junction, both are not at the same position. And the metallurgical junction is in between the transition region of this electrical region. So, if the electrical region is in between, the junction metallurgical is region, which is a physical junction between the two, may be in between these two. The predominant cause of this is the auto doping, which shifted the metallurgical junction. For example, some of the p-type layers are escaping and getting introduced into the epitaxial lesion, which is when we heat some of the p-type dopants. Due to the more energy, when it is heated, the p-type dopant will be moving into the n-type into the uh, n-type epitaxial layer. So with the heating, the p-type dopants will escape. It will evaporate and modulate the gas stream before the epitaxial growth. So the junction is shifted, which we can say like this one. Here the junction is ideal junction, which is metallurgical junction, which we require is over here. Here this is the bulk material and this is the epitaxial material. So actually we want this ideal conditions junction, like this is n type and this is p type, or this is n plus type or n type as here. So the junctions may be shifted due to the auto doping from for the shift of the dopants. The dopants may move from over here to the here, and it gives the actual junction from shifted by this side. So to the shift of the dopants, the electrical junction will be different from the actual junction. Similarly, in the gas auto doping that we have covered in the main lecture series, gas auto doping will be from the gas to the p-type layer. So the junction concentration will be decreasing and it will be going like this one. So the actually junction shift will be there. So if we see from this, this is referred from the and it is so from this, if we see the junction shift, as we have seen that the gas phase auto doping will be decreasing. The second the second defect that is created due to is the buried layer. The buried layers are usually are there when we have a well-shaped structure of the device. When we fabricate like well-shaped BJT, one or more diffusions are applied to substrate so that we can have we can create a layer of collector, emitter, and the base junctions. So to create these, we have to diffuse more times p and n type of the layers. These diffusions, when applied to the substrate, uh, these may create the diffusion under the film. Those are called the buried layers. These diffusions are generally done before the oxidation and the ion implantation that we have discussed in the main lecture series. So using lithography, we have to diffuse these different type of the layers. So these diffusions, when created, are called the buried layer. The other name is the diffusion under film. The layers that are created by the diffusion are the diffusion under film. The presence of these buried layers are complicated the epitaxial layer because uh, its effect on the auto doping and the results in the defects. The defects may be the pattern shift or the pattern distortion. So the pattern shift is when there is an indentation of the surface, that is a step on the surface, and if we grow an epitaxial layer that is of the same stage, that will be transformed into the epitaxial lesion. if the growth of this epitaxial layer is aligned with the step, the epitaxial should layer form a step. That is, the layer formed will be of a proper alignment. These steps will tell us whether the underlying buried layer is, and we can properly put on the base mask and the emitter mask for the fabrication. For example, if we let's suppose if there is a this well shape and we want a layer grown over it for the uh, emitter, collector and the base regions, the layer that will be grown over here will be like this one. So it is shifted by some reason, and when it is grown over a layer is grown over it, it will be shifted by like this one. So the layer will be shifted by some reason. This is due to the diffusion that we have discussed in the main lectures. So this will give a shift in the pattern. So the layer that will be grown over the other layer will be dependent upon the pattern that are created in the lower layer. So like here, if we see there, this is a layer that is, this is the substrate that we have created, and another layer is created which is a buried layer for the creation of the junction. Now, when another layer is grown over here, due to the diffusion, buried layer, this layer, the layer that will be epitaxial layer, that will be shifted by some value. Let's suppose this is delta x through which this has shifted, delta x. So we want it to be here, but it is going by here. So there is a shift of the pattern in the overall pattern of the device. This is called the pattern shift. The length of the buried layer diffusion was assumed to be x, and the length of the step may be delta x. So the step is of x plus or minus delta x. The pattern on the substrate may get shifted by the amount of delta x, and it can get distorted an amount by delta x. So this is the pattern shift or the pattern distortion. Whenever there is a step on the surface, we are exposing a number of crystal planes at the step, and epitaxial growth takes place isometrically. Growth rate is dependent upon the crystal orientation, so we do not have the overall growth which will be uniform. For example, again if we see here, if the crystal is oriented like this one, the crystals, this face is visible over here, these edges are visible, and at this place these edges are visible, where the lattice structure is not uniform. So due to the different lattice structures at the top and the side, the deposition due to the diffusion will be different. So due to the different diffusions, different depositions, the pattern will be getting shifted. This shift may be give the distortion in the pattern, that is called the pattern distortion. So first thing, to minimize this pattern shift, uh, that means that if we want to have a proper alignment in the all layers that are grown, the first thing is to maintain a deposition temperature uh, which is not a high, uh, which is at a high temperature. So when we are depositing, we should maintain high deposition temperature. High temperature, with the high deposition temperature, the surface mobility of the ions will be high. So whenever there is surface mobility high, the growth rate will be isotropic. This is because the molecules will have enough time to get oriented themselves toward the lower layers. So when the growth we reduce the growth rate is again will be isotropic, because this will give the time for settlement for the ions or the for the gas molecules, which will minimize the pattern shift. So it will be the growth rate which will be reduced to maintain the pattern. Another thing is the lower temperature. When lower pressure. When the pressure will be lower, the gas molecule uh, will be have lesser concentration, and it will give lesser mobility, and the deposition will be more. Another factor is the substrate orientation. For the 100 orientation, the crystal plane is easier to have the minimum pattern shift. Wherever if we have 1 pattern, generally there is a misorientation which is by 2 or 4 degree. So if we misoriented these 111 wafers by 2 or 4 degrees, there will be pattern shifted will be minimized. So accordingly, we have different type of uh, mm, different type of locations, different type of distortions that are will occur in the epitaxial to the layer. These are the general description of the layers due to the autodoping, and the buried layer that we see. So here we see that this is a buried layer that is created between the epitaxial layer, and due to the diffusion over here, over this region, there is a buried layer that is created. There is a buried layer that is created. There is a gas autodoping that is created. So we have to create an layer over here, which is the epitaxial layer, and there may be a substrate that is again that is also doped by the arsenic layers. So the mainly defects on the epitaxial layer are dependent upon how the bulk layer has been created. The bulk layer orientation will define the epitaxial layer quality. So the defect that are present in the bulk layer, that will transferred that will be transferred into the epitaxial layer. So for example, if there is a dislocation in the wafer, then this dislocation will be transferred into the epitaxial layer. So there will be a edge dislocation in the epitaxial layer. So in edge dislocation, an extra amount of half plane of the atoms, which is viewed as 2D, is an extra line. This line will extend to the epitaxial layer. For example, if the layer grown over one layer is to the another layer is by some pattern shift, so you can see that there is a alignment, there is a misalignment from the 1 to 2. The second layer will be again misaligned by some another portion. So if the orientations, if the crystal is oriented by half plane, so if this is a body centered plane, if we grow a layer over here and that is oriented, that will be growing, that may grow like this one, or it may grow like this one, where this line will be there. So these atoms will make a extra half of the dimension, half of the lattice over the half of the plane of the atom away from the main layer, substrate layer. So when again it is grown, when another layer is grown over here, that again will be orienting in the same way, and it will give the another edge dislocation. So edge is bending somewhat inward or the outward, so it depending upon the orientation or the deposition of the atoms over the previous layers. The second type of the fault is the stacking fault, which is generally due to the some non-reactive material present, for example the oxides present on the surface. So when if this is a surface, when there is a oxide present over here, when gas will react, gas will passed over here, passed over this one for to react, for example in CVD, if the gas is passed over this molecule, so that that can deposit to make epitaxial layer, then there will be no reaction over here, and the gas will not deposit over here, for example silicon epitaxy. So when this will be not deposited over here, later on it will be grow like this one. So the epitaxial layer grown over here will be like this one. This is due to this oxide that is present over here, that will not allow to other layer to be grown over here. Third type is the during the epitaxial growth, if some contamination is added, that due to some impurity present in the gas steam in the chamber. These contaminations may be giving a extra amount of dopants, or it may be distorting our electrical shifts. So this will giving all the possibilities. Next is the hillock or a valley that may be present in the epitaxial layer, which may be due to the presence of the other type of contamination in the wafer, or it may be present due to the uh, irregular concentration of the gas. The fifth type of the fault is the bulk stacking fault. This is actually crossing the region of the epitaxial region and is grown into the epitaxial layer to form a layer of the stacking faults. If we conclude all these things, these can be summarized like this one. First is the edge dislocation. First one is the edge dislocation, where this edge dislocation is the due to the extra amount of the half plane that is exposed during the deposition of the on the wafer. Second is the stacking fault, which is due to the oxides present in the substrate surface. Third one are the contaminations. Fourth one are the hillocks, which are due to the irregularities of the concentrations. So whenever their concentration will be higher, there will be more deposition than the regular deposition, which will be giving the hillock. Then stacking fault, which is due to the some impurities present, which are gone into the vapor. So if some some impurity, some contamination has gone from epitaxial layer to cross the epitaxial layer and gone into the vapor, then that will create an stacking layer. So if this is, for example, if this is a contamination that is present over here, this contamination will attract, this contamination will, for example, if this is a positive type of uh, contamination that is present, for example negative dopant that we need to dope later on, if those are present over here, those will attract the negative type of the contaminations. So negative ions that will be over here, that will be attracted toward the wafer, toward the substrate, and these negative type will go into the epitaxial layer. These may be crossing the epitaxial layer because there is a attraction force between this positive and the negative. So it is crossing the epitaxial layer and going into the substrate. So these are the 5 major defects that are created during the depositions. Mainly this is due to the uh, auto doping, for example, and the crystal orientations. So in this lecture we have discussed the 5 type of the defects. We have also discussed the buried layers and uh, the reduction of the buried layers. Mainly the reduction of these defects are by the higher temperature with the higher mobility and the lower pressure. So we prefer LPCVD, which we have discussed in the main lecture also. So all these can be reduced. All these can be reduced by maintaining a proper clean chamber. The proper type of the gas that is to be present in the chamber. Third thing is to lower down the temperature so that uh, the stacking fault and the edge dislocations can be lowered down and reduced. So this is about the defects in the epitaxial layer.